Okay, for those people that are been absent for the lab, here's the data I want you to use, and here's what we did. We took a tuning fork. We took a whole series of tuning forks with different frequencies on them, and here's a tuning fork, and you can see that it's got 256 written on there. That's the frequency of the tuning fork. And if you strike the tuning fork and put it down on the table, you can hear it makes a nice pleasant sound. That's 256 hertz. That's a C note. And then we did this for a variety of tuning forks. And then the speed of sound is equal to V equals the frequency times the wavelength. We just solved that for the wavelength, and all these tuning forks here make sound at different wavelengths. Now what we found is that if we held this tuning fork over closed pipes of different lengths, they would resonate at these lengths right here. Now if you were absent, you need to come in and see this demonstration, but these are the data you get. So use these data. Okay, now we took these data and we graphed, because here's the question. We want to know, how does the length of a closed pipe that will resonate with a tuning fork depend on the wavelength of the sound made by the tuning fork? It's kind of an awkward question, but that's what we're trying to answer. And so we calculated these wavelengths based on our known speed of sound. And then we actually experimentally measured the length of closed pipe that will resonate with these tuning forks. These are all in meters. And then we graphed them. And when we graph those data, and I want you to graph the data, here's the length of the pipe, and here's the wavelength of the tuning fork. We graphed the data. We drew a straight line through them. We found that it had a slope of 0.25. So the length of the pipe is equal to 0.25 times the wavelength. And this answers our question, by the way. So let's do that. Write your conclusion. Basically the question was, how does the length depend on the wavelength? So we can say the length will be 0.25 times the wavelength for a closed pipe resonator. Okay, that's our conclusion. Now what I want to do is show you why this is true. Okay, and I've got just enough time to do it. So let's talk about why this is true. And what you have to do is use your imagination a little bit, have little cartoons running through your head. Okay, and I don't know what you're looking at, Chad, but could you look up here? All right. So let's do this. This is the consensus. Now, here's what we did. Here is a pipe that I had dipped in the water. And so here's the water level right here. So what the water does by lowering or raising the pipe in the water, here's the graduated cylinder I had it in, and so here's the water level. By raising or lowering this pipe, I could control the length of the closed pipe. And I'm going to call this length L from here to here. Now, when you have a tuning fork over the top of this, and here's my tuning fork, okay, this tine, right, this is called a tine, is moving down and up. It's vibrating very quickly. And I can show that to you here. See how it's kind of blurry? It's blurry because it's moving up and down 256 times every second. Now we're actually going to look at these under a strobe light. It's going to be really amazing. Okay, later on. So the tuning fork goes up and down. Well, we're going to look at the tuning fork when it's down. So here's the tine, and what the tine does is the tine vibrates up and down like this, 256 times per second. But when it goes down, it crushes the air. It pushes the air together, creating a compression. So I'm going to represent a compression by showing a series of dots. So imagine that is air molecules pressed closer together. Pay attention to this, please. Now this compression moves down at the speed of sound. Now remember, the air molecules themselves do not move all the way down the pipe. It's the compression that moves down the pipe. Just like when I squish in the slinky, right? It was the compression that moved through the slinky. This is going to move through the air molecules all the way down to the bottom of the pipe. So let's draw this again. So imagine the air molecules. Here's the water level. So here's the water molecules and, the air molecules that are squished in the compression. The compression moves through these molecules. And then what does it do? It hits the water. So here is the pipe again. And now the compression squishes into the water. Okay, and it bounces off. It reflects off the water. And then it moves its way back up the pipe. So here's the water level again. And now here I show the compression moving back up the pipe. So it moves down the pipe, bounces off, moves up the pipe. And then what does it do? And this will be the last one of these I draw. The compression actually comes out of the top of this it's closed on the bottom end, but it's open on this top end, and it goes out into the world for us to hear. But what we notice is that the sound is getting amplified. Now here's what I want you to think about. If for the sound to get amplified, I need a resonance. I need this compression to get compressed even more. I need the magnitude of the amplitude. I need the amplitude to get a lot bigger. I need more compression. So if I've got it, everybody think right now. Look up here and I want you to think. I got a compression going out into the world. What do I want the tuning fork to be doing at this instant in time when this reflection comes out of the pipe? Huh? No. Because if it was going back down like this, what does the tuning fork create on this side? On this side out here. It stretches the air out, doesn't it? And it creates a rarefaction that goes out into the world. Well, if the tuning fork was back down, the rarefaction it makes would actually cancel out the compression that's coming out of the pipe. So we don't want the tuning fork to be going down like this. No. In fact, what we want it to do is to be going up. And I'm running out of time, so I'm going to go faster. We want the tuning fork to be doing this. Because that way, so it was down like this, but then we want it to go up like this, and we want it to be in the upward maximum part of its amplitude when this reflected wave comes out of the pipe. Why? Because that way its compression constructively interferes or piles on top of the compression that came out of the pipe. And so what happens is you get a very highly compressed wave of air or coming out of the pipe, and it sounds louder. So we want the tuning, in the time it took this wave, this compression to go down the pipe and back up the pipe, we want the tuning fork to go through half of a cycle. Vroom. Okay, now I'm going to give you a chain of logic, and you've got to follow the chain of logic. For the tuning fork to go through half of its cycle, that means I have this wave has enough time to travel half a wavelength of sound. Half a period means it traveled half a wavelength. So that means that this distance plus this distance equals half a wavelength. That means that L plus L, that is 2L, twice the length of the pipe, because it has to go down the pipe and back up the pipe. We want it to be equal to the distance that the wave travels in half a wavelength. Half a wavelength. Does that make sense?
Yes.
Well, now let's solve for L. What do we get? L equals the wavelength over 4. And what is 1 over 4 equal to? 0.25 times the wavelength, which is exactly what we got. So look, we did this experimentally. This is our empirically derived equation for the length of a closed pipe that will resonate as a function of the wavelength of sound made by the tuning fork. Here is why it happens. Because the tuning fork only has enough time to go through half of its cycle. That's half a period. How far does sound go in half a period? Half a wavelength. So the sound goes down the pipe and up the pipe and goes half a wavelength. Well, that's twice the length of the pipe is equal to half a wavelength. That means the length of the pipe is equal to the wavelength divided by 4, or 0.25. And that is why the sound resonates, if it's at just the right length with a particular tuning fork. Any questions? Okay, so this is our relationship. L, the length of the pipe, equals the wavelength over 4. That is all.